What's up, everyone? It's me, Miss Wesley, and it's good to see you here for Precalc. We are in the beginning, still in the beginning of our Basics of Trig unit, and I want you to think back to some other things that you've seen before in other math classes about angles and angle measurements. We've talked about how you could look at an angle like the one you see in this warm-up. So I am in your Trig Packet 1 on the top of page 7 to talk about radians and degrees. But I was just going to ask you, this is a time where it'd be good if you were in front of me because I'd get members of the class to tell me what do you think you could call this angle measure? And some people might say, it looks like it's about 30 degrees or so, right? Or some might tell me it looks like a big, huge angle measure above 180, above 270. It looks like it's more like maybe 330 degrees, some might say. My first question is, while we're still talking degrees, is there a possibility of calling this a negative 30-degree angle? And this is what I want to get into first. We have a little bit of terminology on this page and angles vocab. So get yourself ready to take some notes and we'll walk through some practice problems. While you're doing that, I like to start things off light with a joke. So where's Waldo? Why? This is a classic. Why does he always wear stripes? Well, it must be because he doesn't want to get spotted. Okay, back to business. Angles vocab. There is a way to set up an angle, and we call it standard position. I'm going to put that in the first blank. Standard position when we talk about angle measures. Angles have two sides, right? You've got an initial side that's going to be right on the positive x-axis, and then you have this terminal side that when we put this on a coordinate plane, it could land in any of the four quadrants. This one happens to land in quadrant 2. Now, today we'll be talking about negative and positive angle measures, and it all just, the difference is going to be the way that you rotate. If you rotate from the initial side counterclockwise, that's your positive angle measurement, right? That's what we typically see here. So counterclockwise rotation from the initial side generates, we're going to say, positive angle measures. Positive, we'll say, angles. Little fancy angle symbol for you there. And clockwise rotation, going the other way, like this beta here, is going to generate negative angle measures. So I'll say negative angles. So you could have named the angle in the warm-up with either a positive or a negative degree value. Angles that have the same, okay, so this is a big one too. There are an infinite amount of ways to name this little angle alpha here. I could name it, 20, 30 degrees, or I could think of this bigger arrow. I could go a full revolution around the coordinate plane, a full 360 and a little bit more, and still land in that same terminal spot. So they call these two amounts of rotation, they say that they generate coterminal angles. Coterminal angles, they look exactly the same. Same initial side, same terminal side, just different amounts of rotation around the origin. And that number, 360 degrees, becomes really important with coterminal angles because I could add or really subtract any integer multiple of 360 and get an angle that lands in the same spot. We'll see that below. Angles in standard position, these are big ones too, just a little bit more vocab here. The angles like 0, 90, 180, 270, 360, they're going to be called your quadrantal angles. So I'm going to that's a little sloppy there, quadrantal angles. Hopefully that word quadrantal reminds you of the quadrant lines, right? Because those are the angles that separate the four quadrants. We know we've got quadrants 1, 2, 3, and 4 going around counterclockwise from the first top right quadrant. 3, whoops, a little sloppy 3 there, looks like a 4. And then 4, IV. And you've got those measures that we mentioned separating the quadrants. So 0 degrees is called quadrantal, 90 degrees if we refer to that. 180 is a big one. Gotta love 270. And then we've come full circle, pun intended there, right? The whole way around the coordinate plane to get back to 360. And you could keep adding, 90 degrees from there. 450 is also going to be coterminal. A couple of these I want to try and sketch. 120 shouldn't be too tough. Put your initial side on the positive x-axis, and then I don't need this to be exact because I'm not having you pull out a protractor. What I need is for the terminal side to be in the correct quadrant and that we draw a little arrow to represent the correct amount of rotation. So with 120 degrees, you haven't gone too far past 90, right? But you're not quite to 180. this would be a quadrant 2 angle, a 120. 590 is another story, right? This is past 360. If you want to think about how far past, just subtract 360. We could take 360 degrees away from this to get a more manageable angle measure where we can find a quadrant for it. So subtract 360, you get down to 230, should be. So that's going to be where? Well, I'll put the initial side on the positive x-axis. I'm past 90, I'm past 180, but I'm not quite to 270. So if you could give me a quadrant 3 angle, that would be good. And when we draw the amount of rotation, can you represent that you've gone a full 360 and then all the way back around again? That's the fun part, is drawing that loop-de-loop down to quadrant 3. Which one of these negative angles could we do? What if we did, let's try 3 and 4. What if we did negative 150? Well, you still start on the positive x-axis. So our initial side's still at 0 degrees. Then think about going negatively. You're not quite to a negative 180, but you're pretty far past the negative 90, right? You'll go past 270. So give me something that's not quite to 180 this way, and we'll draw our arrow of rotation clockwise instead of counterclockwise. A negative 720, that looks like I sniff a coterminal angle, right? You could add a couple 360s to that, and you're back at 0 degrees. You go 360 in the negative direction once, you go 360 again, almost getting dizzy here, and you're back to 0. Drawing this angle, you really just, the initial and the terminal side are the same exact measure, that this is coterminal with a 0 degree angle. But if you think back, and you turn the page, if you think back to the olden days, we had this other measure that's going to become crucial to work with later in pre-calc and then into calculus next year. You're going to see radians much more than you've seen degrees. So now we got to get track of, okay, refresh our memory. What do we know about radians? We want to look at converting between radians and degrees and looking at them with and without a calculator. So here's where it gets fun. It says, well, what is 1 radian? Well, radian to me sounds like radius, right? The word radius of a circle. So I'm going to write radian in this first blank. 1 radian, it says, is the measure of a central angle that intercepts an arc S equal in length to its radius R. So imagine this circle, and I've got a length of the radius here. Imagine that's like a red piece of string, right? I could pick it up, and it would be floppy, and I could fit it around the circle. And we're kind of talking about how many times you could fit that radius around the entire circle, a full revolution. Well, here, if S equals R, another thing you could say here is that theta always equals S over R. And 1 radian, right, is the angle. I'll put a theta in here for the angle. That is the central angle when you've gone 1 radius for this arc length. I want to count how many times that radius should fit around the circle. So if I wrap that piece of string, let's see, I've got 1 radian. So I've gone up in quadrant 1. I take this string, I get a second radian here, 2 radians. I've got 3 radians. Notice I'm almost to 180 when I'm just at 3 radians. A little bit more gets me to 180 degrees. Here's your 4th radian. Here's 5 times you fit that little piece of string around the circle. Here's the 6th time, almost 6 and a little bit of change. Gets you back a full circle, all the way back 360, or you could say 0 degrees. If you recall, right, what we can say is, because I want to talk about the conversions here, the measure of, we'll say a measure of 1 degree. So 1 degree, it says, is equivalent. Well, since an entire circle to get from, from the positive x-axis all the way around, you have to go 100 or 360 degrees. 1 degree is 1/360th of a complete revolution around the vertex of that angle. And since 1 complete revolution, do you recognize this 6 and a little bit of change? It's actually more, a better approximation would be about 6.28. I know that's not exact, but it's pretty close. And remember this distance, once you got the radius 3 times around the circle, you were at 3 and a little bit more. Recognize the approximation 3.14. I'm hoping this rings a bell and brings back happy memories of previous years when you've used radian measure. You're 0 radians here, and over at 180, you're at exactly pi radians. So to refresh your memory, halfway around the circle, just to get over to this line here, you have to go pi. And likewise, 6.28, good approximation for double pi. Once you've gone a full 360, that gets you to 2 pi around the circle. So I'll put that down here too. 360 degrees is going to equal 2 pi radians. I'll just put RAD. The cool thing about radians, though, If I haven't been particular enough, and I bet that I have in class, if you're giving me a degree measure, you must put the units on it. How am I going to know this is 360 what unless you put that degree measure there? Sure, I wrote RAD here, but for a radian measure, a lack of units implies radians. So I don't really need to write RAD by that 2 pi radians or that pi radians here. And what we see more often is 180 degrees. If we divide both sides of this equation by 2, just gets you pi radians. So you could say simply pi or pi radians there. I want to fill in a few more measures, not all of them, around this circle and see if we can get into some conversions, because we'll be in really good shape if you could look at any angle measure now and figure out what it would be in degrees and what that is equivalent to in radian measure. So what? You can kind of, and this is another pun intended, you can divide up this circle like pieces of pi, P-I-E. But what? If I go 0 to pi, that's, I've gone 2 quadrants. If I'm only halfway up here at 90 degrees, that equivalent in radians should just be pi over 2. We should have just gone half pi. So 1/2 pi, 2/2 pi. Let's get down to the bottom of the circle. Down here at 270, we've gone 3/2. So I'll say 3 pi over 2, like that. And then back to 4/2 pi. I'm over to 2 pi when I've gone full circle. I can also, if I were cutting this up like a pizza, I'm sure I would be splitting it into more pieces to be able to share with people. So let's go green here. And what if I went just halfway between 0 and half pi? So if I cut half pi in half, I get at 45 degrees here, I get a 1/4 pi, pi over 4. And just for fun, we could keep counting 1/4 pies and get ourselves all the way around to each quadrant, right? So multiples of your 45 degrees. 1/4 pi, 2/4 pi. Over here at 135, I'm at 3 pi over 4, 3/4 pi. Okay, we'll work our way to the bottom. Let me move myself out of the way. Then we go 4/4 pi, 4 pi over 4 is just pi at 180. And then 5 pi over 4 we can put here. This is down at 225 degrees. You've got 6/4 pi is down here at 3 pi over 2. And then here's 7 pi over 4. That's right where 315 would fall. And then we're back to 2 pi. We will also be focusing on pi over 3 and pi over 6, but I'm going to save that till a later part of the lesson. So let's see how we could convert. This is something that's good to keep track of. To convert between degrees and radians, you could always multiply degrees by some fraction that equals 1. So since you want radians, you want pi in your answer, you could put pi radians over what it equals in degrees. The conversion would be to multiply by pi over 180 degrees. And then if we need degrees, right, we could take our radian measure. If we had to convert the other way, we can multiply by the reciprocal of this. We could take 180 degrees and divide by the pi radians, like that. So let's practice with a little bit of conversion. So it says convert to radian measure. 30, 45, 60, those are huge angles that come up a lot. 30 degrees, take 30, multiply. You kind of want pi in your answer when you want radians. So it's a good idea to multiply it by the fraction where pi is up top, right? That's a good way to remember it when you're going to radians. And I don't want you to reach into a calculator for this. I want to leave pi in your answer. So we would just have to reduce 30 into 180, and that goes in 6 times. You could say that's just like saying pi over 6. So if I ask you about 30 degrees or if I ask you about pi over 6 radians, those are one and the same. 45 degrees we just saw. Here's the conversion, but we saw it already as a 1/4 pi. It was halfway to half pi, pi over 4. And 60 degrees, right? That could be double, should be double 30 degrees. So you could either multiply by pi over 180 like we've been doing, or just double the answer that you got for number 6, right? And instead of pi over 6, it should reduce to pi over 3. For a similar reason, you'll see that 90 degrees becomes half pi. We saw that on the circle that we drew above. And here's where I want to just grab a calculator. I see a degree measure that's in DMS, degrees, minutes, and seconds. So I'll reach to the calculator, and I'm going to multiply and use the pi key in my calculator too. So what was it? I think it was 249. And then if I don't want to go to those DMS keys, I can add that. So I know that it was 32 minutes. There are 60 minutes in a degree, so divided by 60. And then I could say add the number of seconds, 47 seconds by the 3,600 seconds that are in a degree. So it's this degree measure, and we want to multiply by pi key over 180. See if I can fit it in. and write that down. Write 4.355